Thank you for the very interesting presentations of the two previous speakers. I'm going to present the title, the very promising title, Towards Closed Loop System in the Steel Industry. I personally thank worldsteel and Nahi to give me a opportunity to present here. The design, the cover page, was designed by one of the Korean designer, which was used in the Asian Steel Watch, which was published in June. So this is a circular image of steel. So use it for whatever you want. All right. I briefly go over the introduction from open to closed loop, and then current status and challenges in the steel industry, then towards closed loop system for the steel industry, then concluding remarks. Circular economy is being accelerated as the fourth industrial revolution progresses, along with the energy transition and resource revolution. Since the first industrial revolution, companies and consumers have largely adhered to a linear model of value creation, as you see in the bottom. Resources are acquired, processed using energy and labor, and sold as goods, with the expectations that customers will discard those goods and buy more at the time. However, as we are facing energy transition from coal to renewable, such as solar and wind power, resource revolution is combined with environmental challenges, moving towards more sustainable economy, so-called circular economy. Moreover, as we are entering the age of the fourth industrial revolution with digital data technology incorporated, a systemic shift towards the circular economy is already beginning to take place in a foreseeable future. New technologies and data platform enabled by the fourth industrial revolution will expedite the transition to a circular economy. Just like any other paradigm shift in the economy, the most important enabler of the transition to a circular economy is the advance in technologies. The fourth industrial revolution and newer technologies associated with it will accelerate the transition to a circular economy. Accenture identifies 10 disruptive technologies in this regard. We categorize the technological needs for the circular economy as 4 types. First, advanced collection, sorting, and recycling technologies. Second, efficient material processing technologies. Third, production technologies that support design for circularity. And the fourth, interactive platform for enhanced connectivity. Especially interactive platform and connectedness such as machine-to-machine and IoT will become a level playing field in near future. These technologies are maturing fast and provide concrete benefits to enable circular economy businesses. This is very familiar stages of recycling. Basically, circular economy is based on closing the loop through 6 stages of recycling. In here, we call it 6 R's of production. Worldsteel uses it as a 4 R's, and some others use it as a 9 R's, 3 R's, but we basically classify those stages as 6 R's. Advancement in circular technologies and data platform is closely linked to every stage of upcycling in a closed loop system. In simple terms, circular economy seeks to eliminate any kind of loss and waste in the market. It can be delivered through 6 R's of products and materials in every value chain, which is linked to the circular opportunities or business models. Recently, in addition to recycling, there is a strong focus on the other activities for intensifying resource use and extending lifespan such as repair, refurbish, reuse, and remanufacture. In order to cope with shifting to a circular economy, it would be the starting point to understand the current status, advantages and disadvantages, limitations and challenges of the steel industry. When we look at steel from a circular perspective, steel has many circular advantages such as infinite recycling without loss of properties, permanent material, and easy separation and recovery. First of all, as the steel industry has invested to develop new grade of advanced and ultra-light strength steel, we have reduced steel weight in many applications to manufacturing, such as auto sheets, by up to 40%. This contributed to improving fuel efficiency and reducing CO2 and NOx emissions. In consumption phase, the large portion of steel is used for buildings and infrastructure, which have a long service life up to 100 years. It has a long lifespan compared to other materials such as aluminum. Recycling is steel's fundamental advantage. Steel is superior in terms of quantity and quality of recycling. Steel has a high recycling rate ranging from 70 to 90%, advantages of infinite recycling without loss of properties in principle, and easy separation and recovery. However, steel has relatively high environmental impact in its production phase compared to other key materials. This slide is a little bit different from what Mr. Lemons presented, some numbers. It was based on the publication data by Economist and WBS CSD, roughly almost same, but some are different. The table estimated by these institutions shows that the material volumes and their carbon emissions and water and land footprint of 8 key materials in the circular economy. While steel accounts for 9% of the total production volumes, it is responsible for 23% of global greenhouse gas emissions and 2% of water consumption. Compared to aluminum, plastic, cement, and glass, steel has a very high carbon intensity. Therefore, from an environmental point of view, carbon is a steel focus area to make a stride for the circular economy. This is a kind of a scrap circulation diagram, maybe using the blast furnace and EAF. Scrap recovery rate varies from 50 to 90%. Actually, we created this diagram, but we collected some of the data, but it's not still sufficient. There are still considerable losses of material and energy with each stage of production and use. In terms of material flows, around 650 million tons of steel scrap every year, saving 945 million tons of CO2 annually, are recycled according to worldsteel. Today, 30% of all new steel products are made from recycled steel. However, if we consider the whole life cycle, including steel-consuming industries, scrap recovery rate is from time to time far below 100%. There are still considerable losses of material and energy within the steel-making boundary, as well as with each use cycle. Some studies suggest that more than half of the scrap generated annually is inevitable to be downcycled or downgraded for a considerable period in the future. One thing to point out is that there is still a paucity and complexity of data for describing steel materials flow in society. There is a great need for filling the data gap and understanding the whole picture of the steel materials flow in detail, which should be essential, the essential base to step forward to closed-loop recycling system. Then it brings us to the question, what causes circular leakages in the steel industry? Losses and waste are coming from material complexity, geographic dispersion, lack of incentives, and infrastructure. First, material complexity. Steel use in product is diverse with high level of material variation and complexity. It is getting harder to identify, separate, and recycled materials. Second, geographic dispersion is another challenge. The recovery and recycling system is mostly localized and fragmented, and there is also a disjoint supply chain issues. Third, there is a lack of incentives. Despite potentially large volumes of products, there is low intrinsic value of recycled products. Moreover, lack of markets at scale and policies and standards to promote circular economy aggravates recycling. Lastly, we need far more data and infrastructure to support a closed-loop system to close a gap. There is a greater need for digitalization of the recycling chain and data platform. Circular economy will affect not only steel-making processes, but also the entire value chain of the steel industry. The advent of circular economy is likely to bring significant changes for the industry. It will affect not only steel-making processes, but also the entire value chain of the steel industry. As for research and development, it is essential to focus on product development and design based on life cycle analysis and process innovation with carbon-free and zero waste. We need to enhance recycling of raw materials and gradually adopt more substitutable renewables and eco-friendly raw materials. Manufacturing processes have to target minimizing losses and waste and reducing environmental damages using smart tech-based management of resources and waste streams. Products are required to be ultra-light, high strength, and a high performance steel with longer service life and recyclability. In addition, byproducts are considered as a source of revenue stream. In terms of logistics and services, there comes an emphasis on reverse logistics for a wider range of product categories, circular economy data platform, and e-marketplace. Now, in order to understand the value chain impact that the circular economy could have on the steel industry, it is useful to look at some case examples. First case is Nucor. Steel makers, including Nucor, are seeking a response to the global challenges to produce high-quality steel, reduce CO2 emissions, and have a more innovative and sustainable business model, both in terms of environmental impact and financial return. Nucor is one of the leading companies who recognizes process innovation is the key to unlocking the potential. The introduction of minimal resulted in faster manufacturing and less energy-consuming innovation. Moreover, recently micromill enables to increase the efficiency and productivity, which can deliver much thinner strip steel with much less energy consumption and CO2 emissions. Furthermore, it can be more adaptable and applicable to install nearby scrap production sites or customers, so-called decentralized recycling. Let's move to the POSCO case. POSCO is a good example of pursuing product innovation from a circular life cycle perspective. In case of GigaSteel, which was recently developed, POSCO's high performance and eco-friendly steel, it has many circular advantages such as high durability, longer life cycle, and less life cycle impact. In particular, it contributes to CO2 emissions reduction, roughly 10%, when they are used in final products, especially automotive. Postcement, that is developed in 2012, is an eco-friendly cement with a higher slag content. Postcement replaces cement clinker, which contributes to CO2 emissions reduction and demonstrates improved physical properties such as pressure resistance and strength. It is one of the best examples that the waste product is recycled and introduced as a raw material in a different value chain to another industry, in this case to construction industry. Furthermore, in order to accelerate product innovation and provide transparent information, POSCO has established life cycle inventory database for POSCO World Premium products and promoted environmental product declaration certifications. Companies can create values by providing platforms which improve efficient material flows and asset utilization. This slide for Tata Steel's M Junction represents a very relevant illustration. M Junction is a joint venture established by Tata and SAIL in 2001. It provides a digital platform to connect buyers and sellers of scraps, wastes, and idle assets. M Junction has increased its business volumes from $13.8 million in 2002 to $9.45 billion in 2016. Today, it is recognized as the world's largest e-marketplace for steel. For the steel industry, the important value from the M Junction is that it helps to build data-driven recycling markets and improve transparency of the entire value chain. M Junction of Tata Steel is a good example how platforms enabled through digital technologies can help facilitate efficient material flows. Another good example is ThyssenKrupp's carbon-to-chem project, which was presented in some of previous speaker slides. It's a very interesting example of adding value to the waste. It is a case of cross-industry utilization of CO2 as a valuable raw material. The carbon-to-chem project aims at using the emission gases from steel production as raw material to produce chemical products. This is a cross-sectoral collaboration which enables to achieve cost effectiveness by value creation in a circular economy, fossil fuels savings by replacing the conventional feedstock, and significant CO2 savings. If fully implemented, carbon-to-chem can help the steel industry across Germany to reduce 20 million tons of CO2 emissions annually. This project can also contribute to recovering hydrogen included in the emission gases and using it as a source of renewable energy. From the previous case examples, we can recognize that the growing number of steel companies are already implementing the circular economy model to some extent and exploring future opportunities. With this regard, we suggest three main innovations for the steel industry responding to the circular economy challenges and opportunities. First, process innovation, then product innovation, and third, closed-loop steel platform development in the following slides with more detail. Let me start with process innovation. As we are all aware, circular economy and global climate action with the fourth industrial revolution is leading us to eco-friendly steelmaking processes. To cope with these challenges, the steel industry has been trying to develop energy-saving technology, recycling technology, and eventually new steelmaking processes to replace the conventional blast furnace process. Such efforts will continue in the future. On top of this, the steel industry will further upgrade carbon capture and utilization technologies and conduct research on the hydrogen reduction steelmaking process, which will reduce CO2 emissions to zero eventually. Product innovation focuses on maximizing the product circularity and minimizing the life cycle impact of products. Design is critical in saving resources and enhancing product reuse across the whole life cycle. Better design can help to make steel products longer lived or easier to repair, refurbish, or upgrade. It can assist recycling business when they dismantle products to reclaim valuable materials and components. Modular steel building can be a good example. Including design stage, one of the key considerations for companies looking to recycle products is the product's whole life itself. It is important to assess the product's life cycle impact or environmental footprint to identify strengths and weaknesses. Reviewing current and emerging customer requirements and understanding their life cycle implications is another important area. Lastly, there are significant circular opportunities to add values to byproducts such as slags. We need to further improve byproduct recovery rates and expand its use by improving the quality of the materials recovered. It is also necessary to channelize byproducts for commercial applications like slags being used in concrete and road construction. It is essential to establish a closed-loop steel platform, as I mentioned before, a data platform, a data digital infrastructure to increase resource flow efficiency. Many global companies' CEOs, including Google, recognize and emphasize that intelligent collection of information and data and digital infrastructure is at the heart of the circular economy transition. In this context, closed-loop steel platform would allow the steel companies to capture circular opportunities and create new values. Furthermore, it will be an underlying requirement in order to ensure that the steel industry is moving towards the circular economy. From our viewpoint, 4 core modules or pillars are necessary to establish a digital data platform for a circular economy initiative. Material registration platform is to provide materials information, for example, key characteristics, including usage, availability, and any other pertinent qualities. Material e-marketplace is to connect buyers and sellers of waste streams and idle or end-of-life assets. Resources statistics are needed to be linked, as well as environmental performance data and information, such as life cycle environmental impacts. To sum up, the steel industry will face many stumbling blocks in order to achieve a closed-loop system which will bring enormous changes in its value chains. While steel has many circular advantages in recycle, reuse, and remanufacture, we need to recognize that there is considerable potential for improvement. I mentioned those 3 parts in the slides. I'm not gonna go over all of them. But in order to overcome the challenges towards a closed-loop system for the steel industry, we need much deeper collaboration based on a circular economy platform across the supply chain or value chain and among sectors such as raw material suppliers, steel consuming industries, end users, and recyclers. That brings me to the end of my presentation. Thank you for listening.